What if the Big Bang was not the absolute beginning of our universe, but merely the first in a long series of explosions yet to come? Astronomers are currently exploring some truly massive ideas, suggesting that in the distant future, the universe might fracture, tear apart, or even flip at a quantum level into a completely new reality, thereby triggering a second Big Bang. We might already be seeing evidence of this today. From ripples in the fabric of space-time to hidden traces within the cosmic microwave background radiation, these could all be imprints left behind by previous cosmic cycles. If these theories hold true, then the next grand cosmic event might not be a final end, but rather the dawn of an entirely new world. This story is a long one, so let's explore it together in our dreams, but before we dive in, please remember to like, share, and subscribe. So, what exactly does a second Big Bang mean? Most people think of the Big Bang as a unique, one-time event where space, time, matter, and energy were born simultaneously 13.8 billion years ago. However, in modern physics, a second Big Bang doesn't necessarily mean starting from nothing. Instead, it refers to another cosmic scale spark of energy, a reboot, a return, or an extreme transformation sufficient to recreate the conditions of our universe's birth. The original Big Bang wasn't an explosion inside space, but an expansion of space itself. Every point in the universe was once compressed into a white-hot, dense, and nearly uniform state. In less than a second, space expanded faster than the speed of light, dragging matter and energy along with it. At that time, temperatures were so high that atoms couldn't even exist. The universe was a quark-gluon plasma where fundamental particles constantly collided and combined, eventually evolving into stars, planets, and even life. A second Big Bang would recreate this extreme physics, unimaginable density, extreme temperatures, and rapid explosive expansion. The only difference is that it wouldn't be the first time. It would mark a new cosmic era, perhaps arising from the collapse of our current universe, a phased transition in the vacuum, or even the influence of higher dimensional space injecting massive energy into our world in an instant. You can think of the universe as a living entity born in the first Big Bang. If there is a second Big Bang, it isn't a replay of the same life, but the start of a new one, perhaps carrying faint memories of the life that came before. Physicists call this concept a cyclic or bouncing universe. Theoretical research is becoming increasingly fascinating because it offers a way to bypass the singularity, which is one of the greatest puzzles in astronomy. In the standard Big Bang model, if we reverse time, the density and temperature of the universe rise until they reach infinity. This is a mathematical dead end where the laws of physics as we know them completely break down. But if the universe didn't start from an infinite singularity but emerged from a bounce following a contraction, that unsolvable starting point disappears. In this scenario, quantum gravity effects, exotic matter fields, or higher dimensional geometric structures intervene at the critical moment, setting a limit on the density of the universe and preventing it from becoming infinite, ultimately prompting a cosmic bounce. This bouncing process is essentially the second Big Bang. Unlike the original Big Bang, a second Big Bang doesn't mean the beginning of time. It might just be another continuation in an infinite loop. This cycle could consist of countless expansions and contractions, each separated by trillions or even quadrillions of years. From our perspective within one cycle, we would experience this as the total destruction of the universe, where galaxies are pulled together, space collapses, and energy density skyrockets. But immediately following that, a sudden re-expansion occurs, and a brand new cosmic landscape is created. Beyond the bounce caused by contraction, there are other ways to trigger a second Big Bang. One is called false vacuum decay. Our universe might not be in its most stable state, it's like a ball resting in a shallow dip on a hillside rather than the lowest valley. A random quantum fluctuation could push it down into a deeper, more stable vacuum state. The enormous energy released in this process would rapidly form a new region of space, appearing to any observer within it as a Big Bang. The cost? Our entire universe would be erased instantly without warning. String theory suggests another path involving brain cosmology. In this model, our universe exists on a three-dimensional brain floating in a higher dimensional space. If two brains collide, they release massive amounts of energy, causing the brain to undergo a Big Bang-like expansion. In these models, such collisions could happen periodically, creating endless new cosmic cycles. Regardless of how it happens, a second Big Bang wouldn't simply copy the previous script. The conditions of the universe could be subtly or drastically different. In those initial moments, the magnitude of density fluctuations might change, leading to more massive stars or a sparser cosmic structure. Fundamental constants, such as the strength of gravity, the speed of light, or the ratio of electron to proton mass, might also shift, creating entirely different physical and chemical environments. Even the direction of time could be reset. In our current universe, entropy is always increasing. But if a second Big Bang could reset entropy to a very low value, the clock of time would start over for a new era. If it cannot be reset, then each cycle would inherit some of the disorder from the previous one, making the universe increasingly chaotic through its endless cycles. When cosmologists discuss the second Big Bang, they aren't just telling stories, they are focused on the specific conditions, density limits, temperature ranges, and the behavior of quantum fields that could trigger a true cosmic expansion. This is the core of their research. It means we need to measure large-scale cosmic structures and look for faint traces in the cosmic microwave background that might come from earlier cycles to understand how space-time operates under extreme energy conditions. We must also consider the long-term fate of the universe. If energy levels remain constant and space expands forever, galaxies will continue to drift apart until they cross the horizon of the observable world, and eventually, the universe will become cold and empty with no chance for another explosion. That is the so-called heat death, an ending without a second Big Bang. However, the cyclic universe model offers a completely different picture. Don't think of the universe as a single fireworks show, imagine it as a heartbeat, a steady rhythm of birth and death, expansion and contraction, repeating over unimaginable stretches of time. In this model, our universe is just one of many, each born after the death of the one before. The Big Bang was once thought to be the beginning of everything, followed by billions of years of cooling and expansion. But the cyclic model flips the script. From this perspective, the explosion wasn't the initial event, but just the most recent change, the start of the current expansion phase. The basic logic of this model is simple: expansion leads to contraction, contraction triggers a violent bounce, and the bounce starts a new expansion. It is a cycle without a true starting point. Yet, behind this simple loop lies incredibly complex physics involving how gravity behaves at ultra-high densities and the role dark energy plays in each cycle, questions that currently have no definitive answers. In one version of the cyclic universe, gravity dominates initially, while dark energy, the unknown force driving the accelerated expansion of the universe, dominates later evolution. If the strength of dark energy changes over time, the acceleration might weaken, stop, or even reverse. At that point, galaxies drifting apart would begin to converge, and the universe would enter a period of contraction. During this contraction, the universe wouldn't just play its expansion in reverse. Matter would recluster, radiation would grow hotter, and Large-scale structures would melt into a smooth, high-density state. As the collapse continues, temperature and density would soar to conditions similar to the earliest moments of the Big Bang. At this stage, traditional physics would predict a singularity, but in the cyclic model, this point is replaced by a bounce. For example, in loop quantum cosmology, the geometry of space-time is quantized, made of discrete units at the smallest scales. When the universe contracts toward the Planck density, these quantum geometric effects generate a repulsive force that opposes gravity. Instead of everything being crushed into an infinitesimal point, the collapse is halted and reversed into a new expansion. Space begins to grow again, carrying energy and matter to give birth to a new universe. Other cyclic scenarios come from the multidimensional ideas of string theory. In these models, our universe is a three-dimensional membrane, or brane, floating in a higher dimensional space. Another parallel brane might exist alongside ours, interacting with us through gravity. Within this framework, cosmic cycles are triggered by periodic collisions between these branes. Roughly every trillion years, the two branes draw close and collide violently. This impact releases massive energy, heating the branes to extreme temperatures and filling them with radiation and matter. On our brane, this looks like a new Big Bang. Space expands, matter forms, and over billions of years, stars and galaxies appear. We wouldn't see the other brane or the higher dimensional bulk space, we would only feel the aftershocks of this energy. A fascinating feature of this model is how it naturally fits into a cyclic structure. After the branes collide, they bounce apart and move in opposite directions. Then, gravity slowly slows their separation, eventually pulling them back together for a new collision. Each collision acts as a new Big Bang, starting a new cosmic cycle. This brane collision model also attempts to answer problems faced by traditional Big Bang theory, such as why the temperature of the cosmic microwave background is nearly identical in all directions. In the brane world approach, this smoothness comes from a long period of contraction before the collision. By the time the expansion begins, the entire stage has been smoothed out like a flat canvas. Additionally, it avoids the singularity. While moving backward in time in the standard model leads to infinite density, in the brane model, the branes remain finite in size and distance during the collision. The higher dimensional space provides a buffer, so density never truly becomes infinite, resulting only in a finite but incredibly violent release of energy. Verifying a theory based on invisible extra dimensions is extremely difficult, but it does make testable predictions. One is the spectrum of primordial gravitational waves, brane. Collisions would produce gravitational waves, but they would be much weaker than those predicted by standard inflation, perhaps even beyond the reach of current equipment. Another potential clue lies in the details of the cosmic microwave background. Tiny patterns in the temperature and polarization maps might hint at the history of contraction before the collision. Investigations into the large-scale distribution of galaxies might also reveal statistical traces of this slow contraction. The elegance of the brane collision model is that it integrates high-energy physics, extra-dimensional geometry, and cosmology into a single whole. It doesn't require the universe to come from nothing, nor does it require a unique beginning for space and time. Instead, it suggests our universe is just part of a larger, multidimensional dance that may have repeated countless times. Of course, many unknowns remain, whether the motion of branes is stable, if energy is lost during collisions, and how dark energy and initial conditions are set. But these challenges drive the theory forward. In traditional general relativity, the beginning and possible end of the universe are dominated by singularities where density and curvature become infinite and equations fail. Usually, An infinite result is a signal that a theory has reached its limit. Loop quantum gravity provides a way to cross this boundary. It predicts a bounce rather than a singularity. This bounce happens when the quantum properties of space-time itself prevent further collapse and force a reversal. Loop quantum gravity introduces a fundamental new concept: space is not smooth, but made of discrete geometric atoms connected in a network at the Planck scale. There is no space inside these loops, they are space itself. This quantization means distance, area, and volume have minimum units and cannot be divided infinitely. This granularity changes everything under extreme conditions. As a collapsing universe nears the Planck scale, quantum geometric effects take over. This discrete structure generates a powerful repulsive force not from new matter or energy, but as a direct result of quantized gravity. In loop quantum cosmology, the equations of general relativity are modified. When density reaches a critical value, gravity flips from being attractive to being repulsive. This repulsion overcomes the collapse, causing the universe to stop shrinking and start expanding. The result is a bounce, replacing the singularity with a finite, smooth transition. This isn't just to avoid infinite numbers, it leads to verifiable physical results. Some theories suggest the early universe after a bounce might still retain faint traces of the previous one. Anomalous patterns in the cosmic microwave background, especially at the largest scales, might be echoes of this cosmic past life. Loop quantum cosmology also predicts changes in the primordial gravitational wave spectrum. In standard inflationary theory, these waves are produced by quantum fluctuations expanded to cosmic scales. However, in a bouncing scenario, gravitational waves could also be generated during the contraction phase and transmitted through the bounce into the new expansion period. The result might manifest as certain wavelengths being weakened or enhanced, a unique signal. Furthermore, LQC sets a maximum value for cosmic density. In standard physics, density has no upper limit. The closer you get to the starting point, the higher it goes. But in LQC, this critical density is fixed, typically around 0.41 times the Planck density. This acts like a built-in safety feature in the rules of physics, preventing the universe from falling into an infinite curvature. The bounce model also changes our understanding of the arrow of time. In a singularity-centered view, time begins at the Big Bang and has no meaning before it. But in loop quantum physics, time exists before the bounce, just moving in the opposite direction. In other words, the bounce connects two distinct cosmic epochs. One advantage of loop quantum gravity is that it doesn't require strange new particles or energy forms. As long as quantum physics is applied to the gravitational field, the bounce occurs naturally. While theoretically elegant, the mathematics is extremely complex, requiring quantum geometry, spin networks, and Ushtekar variables to describe the evolution of spacetime under extreme conditions. However, LQC faces challenges, such as how to smoothly connect bounce dynamics with standard cosmic evolution like nucleosynthesis, reheating, and structure formation. Additionally, distinguishing traces left by a bounce from those left by inflation is difficult. In many cases, inflation occurring after a bounce might mask or dilute signals from a previous life. Therefore, scientists are studying polarization patterns in the cosmic microwave background and specific frequency bands of gravitational waves to find clues that distinguish the two. If the universe truly undergoes a second Big Bang, there is an unavoidable question: entropy. Entropy is a concept in thermodynamics used to measure disorder. It represents the number of microscopic ways a system can be arranged while maintaining its overall appearance. In everyday physics, it explains why an egg won't unbreak itself and why smoke won't go back into a cigarette. It is the reason we can distinguish the past from the future. Entropy is the arrow of time. The second law of thermodynamics tells us that in an isolated system, entropy never decreases, and the universe is clearly the largest isolated system. This means the total entropy of the universe has been rising since the Big Bang. Every star burning fuel, every black hole swallowing matter, and every supernova increases overall disorder. This isn't necessarily bad for life and complexity, but it's a massive problem for any theory of cosmic rebirth. If a second Big Bang is to happen, it must start from an extremely low entropy state, just like the first one. Only under low entropy conditions can the early universe be smooth enough for gravity to amplify tiny density fluctuations into galaxies and stars. The problem is that after trillions of years of evolution, our universe will be far from a low entropy state. In the heat death of the future, matter will be so sparse it almost vanishes, stars will have long burned out, and black holes will dominate. Black holes themselves possess incredibly high entropy. In fact, the entropy of a supermassive black hole can exceed the combined entropy of all ordinary matter in the observable universe. According to the Bekenstein-Hawking formula, a black hole's entropy is proportional to the surface area of its event horizon, not its volume. This means the larger the black hole, the higher the entropy. To reset the universe, we must face these entropy monsters. Worse still, black holes aren't eternal, they slowly evaporate via Hawking radiation over extreme time scales, but this evaporation doesn't lower the universe's entropy, it just redistributes it until the universe is uniformly filled with high entropy radiation. Some theories suggest extra-dimensional leakage, where entropy leaks into higher dimensional space, clearing our three-dimensional brain universe to create a clean stage for the next contraction. Others suggest that entropy is pushed into regions beyond the observable horizon, avoiding the core of the next bounce. A combination of expansion and de-expansion might also work. After a rapid contraction, space could be extremely stretched, diluting entropy to negligible levels. Brain cosmology offers a partial solution. Its slow contraction phase smooths out irregularities in density and curvature, providing a more uniform starting point for the next cycle. Yet, this still doesn't fully clear the entropy embedded in black holes and radiation. Even quantum gravity's bounce theory doesn't automatically solve this. A bounce avoids a singularity, but how to transform a high-entropy old universe into a low-entropy new one remains an open question. Some physicists speculate that at the critical point of a bounce, quantum effects might scramble information to reboot entropy, but this remains a difficult-to-prove conjecture. There is also the deeper question of why the initial entropy of the first Big Bang was so low. Roger Penrose pointed out that the universe at its start was in an incredibly unique, highly ordered state, almost impossible among all possible energy arrangements. If a second Big Bang is to occur, it must recreate such a state, yet we don't even know how the first one achieved it. Thus, the entropy reset remains more of a hypothesis than a complete theory. If the universe cycles through expansion, contraction, and rebirth, what happens to information between cycles? Does a new universe wipe the slate clean, or is the past preserved? An unexpected answer comes from the holographic principle, which suggests that in the deep structure of space-time, information is never truly lost. This principle originated in black hole physics in the 1970s when Jacob Bekenstein and Stephen Hawking discovered that black holes have entropy. Curiously, this entropy is proportional to the surface area of the event horizon, not the volume. This implies that all information within a black hole can be represented on its surface, much like a two-dimensional holographic plate stores a three-dimensional image. By the 1990s, Gerard T. Hooft and Leonard Susskind extended this idea to the entire universe, suggesting that our three-dimensional reality might be a projection of information encoded on a two-dimensional boundary, such as the cosmic horizon. Applying this to a cyclic universe leads to a staggering possibility: even if a universe collapses and vanishes, its information might be preserved through holographic encoding. When the next universe begins, this information could influence its initial conditions. This preservation mechanism depends on the geometry of the bounce. In brane collisions, information might be stored on the boundaries of higher dimensional bulk space. In an LQC bounce, it might be stored in the states of the quantum space-time network and carried through the point of maximum compression. In either case, the holographic framework provides a way for information to persist through cycles without relying on traditional matter or radiation. This has profound implications. In classical physics, black holes seem to destroy information, but if the holographic principle is correct, information is merely scrambled and stored on a boundary. Similarly, the cosmic horizon might act as such a boundary. Whether it's the surface of a brane or the limit of quantum geometry, information might not be erased. It might become chaotic and unrecognizable, but it still exists. This means the universe might possess a kind of memory. If each cycle retains even a tiny trace of information from the previous one, these faint imprints might still be hidden in our universe today, potentially appearing as anomalies in the cosmic microwave background or strange patterns in large-scale structures. These traces would be incredibly hard to detect. Because information is severely disrupted during a bounce, but they aren't necessarily invisible. Some physicists even speculate that the holographic principle could solve the entropy problem. If all disorder is stored in the holographic layer, the new universe could start physically clean while maintaining a deeper record. This avoids the contradiction of entropy accumulating indefinitely. However, this remains a speculation. The holographic principle was derived from string theory and black hole research. Applying it to the entire universe is far from proven. Even if information is preserved, that doesn't mean it can be read or utilized in the next universe. The most powerful mathematical tool currently available is the AD/CFT correspondence, which shows a duality between higher dimensional gravity and lower dimensional quantum fields, supporting the holographic idea. In a cyclic context, this means the end and birth of a universe might just be two different expressions of the same underlying informational state. In other words, violent contraction and bouncing don't erase information, they re-encode it. This might mean our universe still carries the fingerprints of previous ones. Of course, critics point out that we don't yet know if the holographic principle holds in real cosmological scenarios involving expansion and contraction. Even if information is kept, it might just be a chaotic shadow with no practical role in the new universe. Quantum field theory tells us that stability can sometimes be an illusion. Although our universe appears stable, nothingness isn't truly empty, it's filled with fields, the most critical being the Higgs field. The Higgs field gives particles mass and determines the form of physical laws, but its value might not be permanent. There is a possibility that our universe is in a false vacuum state, like a ball resting in a shallow dip on a hillside when a deeper valley exists elsewhere. In this case, the true vacuum is the lowest energy state. The universe can stay in a false vacuum for a very long time, but quantum physics allows for a rare event called quantum tunneling. If it happens, the Higgs field could suddenly punch through the energy barrier into the true vacuum. This would form a bubble that expands at nearly the speed of light, fundamentally altering the laws of physics wherever it goes. Constants would change, the speed of light, particle masses, and the strength of interactions would all shift. Our familiar chemical and material structures would collapse instantly. Atoms might not form, and planets or life would have no chance to adapt. Most terrifyingly, because it travels at the speed of light, there would be no warning. From a cosmological perspective, this isn't just an end, it could be a beginning. The new vacuum energy density could drive a new explosion, a spark for a second Big Bang. The question is whether our universe is actually in a false vacuum. This is linked to the Higgs boson discovered in 2012. Current measurements of the Higgs and top quark masses suggest we are in a metastable state, meaning the false vacuum isn't perfectly stable, but the decay timescale far exceeds the current age of the universe. Danger is theoretical rather than imminent. However, extreme high-energy events or evaporating black holes could theoretically push the field over the barrier. From a physics standpoint, vacuum decay is a phase transition, similar to water freezing or boiling, but on a cosmic scale. In inflationary theory, different regions of space might exist in different vacuum states, a concept called eternal inflation. Our observable universe might just be one false vacuum bubble among many. Vacuum decay might have already happened elsewhere. If a new vacuum bubble is large enough, its interior would behave like a new Big Bang, with rapid expansion and the creation of new particles. Thus, vacuum decay could be both the destruction of the old and the birth of the new, generating an endless chain of universes. Of course, if the laws in the new vacuum don't support complex structures, the new universe would be a void. To confirm our status, we need more measurements of fundamental parameters. For now, most experts believe that even if vacuum decay is possible, its timescale is so vast that it isn't a threat for the foreseeable future. But in an infinite timeline, a small probability is never zero. The idea that vacuum decay could trigger new expansion brings us back to a key theory: cosmic inflation. In the standard Big Bang model, there are several puzzles: why the universe is so smooth on large scales, why temperatures are identical in all directions, and why the geometry of space is flat. In the 1980s, Alan Guth proposed the inflationary hypothesis, suggesting that between 10 to the negative 36th and 10 to the negative 32nd seconds after the start, the universe underwent extreme exponential expansion. Space was stretched by an unimaginable factor. This was driven by a hypothetical scalar field called the inflaton. In its potential energy well, the field value was at a high point, filling space with a nearly constant energy density that acted like anti-gravity, pushing space to expand at an exponential rate. This smoothed out irregularities and stretched any curvature flat, while tiny quantum fluctuations were magnified to become the seeds of galaxies and the large-scale structures we see today. This mechanism explains the uniformity of the universe and provides a natural origin for galaxy formation. More importantly, inflation makes specific predictions, such as temperature fluctuations in the cosmic microwave background and the potential for gravitational waves. If a second Big Bang occurs, it will likely be accompanied by a similar inflationary phase. Whether triggered by vacuum decay, a bounce, or a brane collision, these scenarios would need an inflationary period to explain the smoothness of the new universe. This suggests that inflation isn't just a part of our history, but a universal feature of cosmic rebirth. Of course, the theory isn't perfect. We haven't directly discovered the scalar field that drives it, and different models yield vastly different predictions. There is also the issue of eternal inflation. In some models, inflation doesn't stop everywhere at once. It ends in some regions to form bubbles like our universe while continuing in others, leading to a multiverse where space is filled with countless independent universes, each with its own physical parameters. If so, our universe is just one bubble, and a second Big Bang might just be the birth of another. In the framework of eternal inflation, new universes are appearing constantly. This might solve the entropy problem. If each bubble is independent, their entropy won't affect one another, and each can start in a low entropy state. But this turns the question toward philosophy. If universes are created infinitely with different laws, why are we in this one? Some use the anthropic principle to argue that observers only appear in universes with parameters suitable for life. Regardless, inflationary theory has become the core framework for explaining the start of a new universe. Whatever way a second Big Bang happens, it will almost certainly need inflation to shape its initial conditions. That's all for today's knowledge sharing. I hope you have a wonderful dream, and I'll see you in the next episode.